Jnanam Paramam Dhyayam. Knowledge is supreme.
Last lecture we have seen normalization lemma and some of its consequences. Today we will have more consequences of normalization lemma, and if there is a time, then we will go to a more refined version of normalization lemma. So, as usual, K is a field and we consider K algebra the finite type. They are also sometimes called affine K algebras or affine algebra over K. So, the next consequence is, if you have let A be an affine K algebra and A be an ideal in Gothi K is an ideal in A, then the radical of A is intersection of all maximal ideals in A which contains A. So, in particular, nil radical of A equal to the Jacobson radical of A. Recall, nil radical of A is the ideal of nilpotent elements of A, which is also intersection of all prime ideals of A, and the Jacobson radical is intersection of all maximal ideals of A. So, one containment is always clear, that nil radical is contained in the maximal the Jacobson radical. However, the other inclusion is may not be correct, because for example, even for ring of integers nil radical is 0, no, not for ring of integers, but Z mod p for example. So, in general it is not true, nil radical could be strictly smaller than the Jacobson radical. So, affine algebra is very important in this assumption. So, proof by passing to the residue class ring A by A, we may assume that the ideal is 0. So, we want to prove that the nil radical equal to Jacobson radical, right. So, by going to the residue class ring, replace A by A mod A, and then we can A becomes 0, and then we want to prove that the nil radical of this ring equal to the Jacobson radical. One inclusion is obvious, nil radical is contained in the Jacobson radical, because nil radical is intersection over a bigger set and Jacobson radical is a intersection over a smaller set. For the reverse inclusion, we will show that if some element is not nilpotent, then it is not here, it is not in the Jacobson radical. That will mean there are no more new elements in the Jacobson radical. So, suppose F is not nilpotent, then I want to show that F is not in the Jacobson radical. That means, I want to show that there is a maximal ideal in the ring, so that F is not in that maximal ideal. So, F is not nilpotent is equivalent to saying that the localization at F is a non-zero ring, where localization at F means S inverse A, where S is the multiplicative submonoid generated by F. Now, because this ring A localized at F is non-zero ring, we know by Krull's theorem there is definitely a maximal ideal. That means, there is a capital this Gothic M which is in SPM of A localized at F. Remember, I am denoting maximal ideals by SPM, and I am not using the notation max A, because that confuses with the maximum. Anyway, so the K algebra A localized at F, this is actually a finite type K algebra, because it is generated by along with the generators of the algebra A, which are finitely many, along with that 1 over F generates that algebra. So, it is a finite type K algebra. So, I can apply the earlier consequence, which I had call it Hilbert's-Null's-Ansatz if I have a field extension which is finite type, then it should be algebraic. So, AF modulo Gothic capital Gothic M, this is an algebraic extension. Now, let us contract this maximal ideal to A. A to A localized at F, there is a natural ring homomorphism, and this capital M, which is a Gothic M, is a maximal ideal in A localized at F. So, I contract it to A, that means consider this small Gothic M, capital Gothic M intersection A. This is a contraction of capital M to A. So, look at this commutative diagram. So, A to A localized at F, this is a natural localization map. AF mod capital M, this is the natural surjective map, and A to A by small Gothic M, this is also natural Gothic M, and K is contained there. So, we have this commutative diagram. In this commutative diagram, this K to this extension, because this is a finite type over K, it is a field, therefore, by HNS this is algebraic extension, and this A by small Gothic M, this is a ring in between. So, if I could prove that this is a field, if A by small Gothic M, if I prove it is a field, then that will mean that the small Gothic M is a maximal ideal in A, and that maximal ideal cannot contain F, because if it contains F, then capital M will also contain F, and that is not possible. So, I have to justify that this A, the subring in between the algebraic extension of fields is also a field. This is what I need to justify. So, let us take an algebraic extension of fields and a subring in between. I want to check that this is also a field. To check that, I have to check that every non-zero element of R is invertible. So, if X is contained in R and K is contained in R, then the smallest subalgebra of R which contain X will also be contained there. So, this K square bracket X is contained in R, but X is algebraic over K. So, therefore, this K small x, this is nothing but it is a residue class of the polynomial ring in n variable modulo the ideal generated by the minimal polynomial of X. So, therefore, we just have to note that the minimal polynomial is irreducible polynomial, because if it is irreducible, it is a polynomial in one variable or a field, it will generate a prime ideal, and prime ideal in a non-zero prime ideal in a PID is maximal, therefore, this is maximal. So, modulo that it will be a field, and we will be done. So, in particular, X inverse will belong to this subalgebra Kx, therefore, it is contained in R, and then we have finished our problem. But we can do little bit simpler than this. So, that is what I have written here, variant. So, look at the subalgebra generated by X, because X is algebraic, this subalgebra is finite dimensional over K, right, because X is algebraic. Then look at the multiplication map by X on the subalgebra Kx. So, it is y going to X times y, right. This is obviously a K linear map, and which is injective because X is non-zero. So, we have a K linear map on a finite dimensional vector space which is injective, therefore, it has to be bijective, in particular surjective, and hence once it is surjective, 1 is in the image, therefore, there is a y. So, that x times y equal to lambda x of y, which is 1, and then y is the inverse. Okay, next one. This is also very important consequence. In general, if you have a ring homomorphism, then you must have seen contraction of a maximal ideal may not be maximal. For example, if you take integers embedded in a rational numbers, 0 is a maximal ideal in rational numbers, but it is not a contraction is also 0, 0 is not a maximal ideal in the ring of integers. But if you assume that it is a K algebra homomorphism of affine algebras, then the contraction of maximal is also maximal. So, that is what this next consequence is. So, for every capital M, which is a maximal ideal in B, M intersection A is also maximal ideal in A. Proof. Again, look at this diagram. A to B given K algebra homomorphism, then go mod capital M, go mod the contraction of M, and then we have these vertical arrows are surjective. This double arrow means surjective. K is contained there, and again by Knudsen dots B by M, which is again finite type K algebra, which is a field, and therefore it is algebraic over this K, and this one is in between ring. And just now we have saw, if you have an algebraic extension, in between ring is also a field. So, therefore, it is a field, and that simply means that the contraction is a maximal ideal. Okay. Now, one more consequence, this I wanted anyway to recall this thing. So, I will take this opportunity to recall the proof of this. If I have an integral extension of rings, then their dimensions are equal. So, dimension of a ring is by definition supremum of R such that there is a chain of prime ideals of length R in A, in spec A. And in one of our tutorial session, I will show you that why this is the correct dimension. I will start with a definition with from a algebraic geometry, and I will show you these forces, these two-way dimension. That is what Krull did it. So, to me it looks like this strange definition. Where did it come from? Right? Because the supremum may not exist, and how do you compute, etc. That is the whole. This course is whole. The first part will revolve around saying how do you compute this. So, the various techniques from local algebra and affine algebra is specially designed to compute this dimension, and when is it finite, etc. Okay, so now I assume that you are familiar with integral extensions, but to be more, I just recalled what it is. So, some basic facts I will recall about integral extensions without proof. A contained in B, then one says it is a ring extension. Also, sometimes you do not need an inclusion, you can only look at the ring homomorphism, and instead of saying integral extension, one can say that the homomorphism is integral, and this is actually a generalization from the algebraic field extensions. So, where the rings are not fields, but arbitrary rings, but we still have to assume they are commutative. So, an element X is integral over A if it satisfies equation of integral dependence. Equation of integral dependence is a monic equation in X, and when you substitute the variable equal to the small x, it becomes 0. Coefficients are in the ring A, where in the case of homomorphism, this obviously this means that you take A, the coefficients are coming from A, means they are images of A under this homomorphism. This is equivalent to saying the A subalgebra Ax of B, this is a finite module. It is generated by, in fact, it is generated by 1 x up to x power n minus 1. In fact, it is a free A algebra. In this case, when we say when B is, every element of B is integral over A, then one says that B is an integral extension of A. So, this in case of integral extension, finiteness, a finite type and finite are, these two concepts are equivalent. So, more I mean to be more precise, integral extension which is finite type, this is equivalent to saying it is a finite extension. Finite means it is a finite as a module. Okay, now some 2-3 very important results which we will keep using in this course, and hence after I will not explicitly state them. So, for example, if I have an integral extension where upper ring is an integral domain, then it is a field if and only if the base ring is a field. Second, if I have a primordial Q in B, then the contraction is also primordial, that is always true, but when upper ideal is maximal, then the contraction is also maximal. If I have two primordials in B, one contained in the other, and after contraction to A, if they are equal, then they are equal. These are very basic facts which you would have learnt in your earlier courses. And now the two most important theorem which are used often. This is called a lying over theorem for integral extension. This is a map. Contraction is a map. Think of contraction a map from spec B to spec A. This map is surjective. This is what the integral will imply. This is just, that means given a primordial in A, there exists a primordial in B, so that the contraction of this is precisely the given primordial in A. The next one is what is called as a going up theorem. If I have two primordials in A, one contained in the other, and I have a primordial in B which lies over the first one, then I can find a primordial Q in B which lies over this the next one, and also it contains the given one. You see, you can always find this surjectivity will tell you can always find a primordial which lies over that, but it should also respect the inclusion. So, this is called going up theorem. Okay, now with this we are ready to prove that if we have integral domain integral extension of rings, then their cool dimensions are equal. So, what do we have to prove? We have to prove that this is supremum of the chains of the primordials in A, this is supremum of the chains of primordials in B. So, I will show you first I will show you the dimension of B is less equal to dimension of A. So, you start with a chain in B, Q1 to Q0 to QR, a chain in spec B, and you just contract it to A, and only you have to check that these are primordials, which is clear, and also we have to check that the inclusion remains, the properness of inclusion remains. That follows from the one of the result what we stated. If you have two primordials, if they are not contained up, or they are not equal up, then their contraction also not equal. So, that shows, now taking over the supremum, that shows that the supremum, so that is the dimension of B is less equal to dimension of A. Conversely, now I have to show that if I have a chain in the spectrum of A, P0 contained in not equal to P1 etc. PR, then I want to produce a chain of the same length R in spec B, but that I will first use the surjectivity of the spectrum. So, given this P naught, I choose Q naught which is lying over P naught, and then now I use the going up theorem to choose Q1 which lies over P1 and which contains Q0. This is a going up and keep going up. Precisely for this reason, this theorem is known as a going up theorem. So, with this we have a chain in spec B, and therefore, dimension is less equal to dimension B, altogether dimension equal to dimension B. For integral extension, dimensions are equal.